Good morning and welcome from NYU. I'm Ted Rappaport, the director of NYU Wireless, and very happy to bring you the second seminar in our continuing series, Circuits, Terahertz and Beyond. Delighted to have you with us on the live stream and also the live audience here at NYU. This seminar series is brought to you by NYU Wireless, and NYU Wireless is supported by a large group of industrial affiliates sponsoring our work here in wireless to Terahertz and Beyond. Today I'm really delighted to introduce you to Professor Josep Jornet. Josep comes to us from University of Buffalo. At University of Buffalo, he's really the interface between communications and nanotechnology, leading the way in plasmonics, and he has some very exciting words and vision to share with us today. We're very grateful to have Professor Jornet with us to help us as we at NYU Wireless aspire to hire faculty, attract students, and grow in this new area of terahertz. Professor Jornet really is a pioneer. He'll tell us some of the things he's done in graphene, where he invented graphene antennas and has looked at how we can do new things up to terahertz and beyond. It's my pleasure to introduce Professor Josep Jornet. Please let's give him a big NYU welcome.
Thank you. Okay. Thank you very much, Ted, again, for the invitation. It's actually my pleasure to be here today and to share some of the work that we have been doing first when I was a PhD student at Georgia Tech, and then since I moved to Buffalo as an assistant professor. The title of the talk today is Terahertz Communication from Nanomaterials to Ultra-broadband Networks. No need to talk much about this, but if you're interested in how we evolve into this field, you can see that we have papers all the way back from 2010 when we were thinking that terahertz was great for short distances. We evolved, we came up with technologies, we identified terahertz as the next frontier for wireless communication, and today we're going to talk about some of the big challenges we have been facing and that we have been solving. Before that, let me explain you my motivation, our motivation as a group to work on terahertz communications, which is like, we will all agree that over the last few years, wireless data traffic has drastically increased due to the way we create, we share, and we consume information. Not only we have more devices, but actually we like those devices to connect at a much faster rate. If we look at the evolution of wireless data rates and we make a prediction for the next 5 years, we will see that wireless terabit per second links are going to become a reality. Of course, we could spend hours discussing about which is going to be the technology that is going to enable terabit per second wireless links, and maybe we would not reach a conclusion. Instead of doing that, what we're going to do is, let's look at the following figure. This is a frequency axis from 0 to 10 terahertz, strategically positioned. Think of all the wireless communication systems that you're using today. Where are they? Well, strictly speaking, they are under 95 gigahertz. And we are talking about everything from your radio, your TV, your cellular systems, Wi-Fi, radar, GPS. What's the result of that? Well, the result is that under 95 gigahertz, we have a rather overcrowded spectrum. Of course, you will say, well, if what you need is more spectrum, let's follow what the people in optics are doing, and let's jump all the way to hundreds of terahertz, where we will have optical wireless systems. And for sure, at optical frequencies, you have the bandwidth, but you also have many other challenges coming from the wireless channel at those frequencies. Whether it's going to be optics, whether it's going to be millimeter wave, the question is, why on earth would you skip 10 very beautiful terahertz band gap? So the terahertz band, what is it? Well, it's everything starting, let's say, from 100 gigas all the way till maybe 10 terahertz before we start with the infrared. And we call this the terahertz band, or in other words, no man's land. Think of the rush for gold. Well, we are in the rush, we are in the quest for bandwidth. Usually we say the terahertz band is no man's land. Is it really true? Well, let's be careful with this. So there are currently no license or unlicensed service rules above 95 gigahertz, but that does not mean that anyone is not using this. Actually, NASA has been and is actively using the terahertz band. You will say, why NASA is using the terahertz band? Well, approximately 98% of the photons that are now reaching Earth emitted in the Big Bang are actually in the terahertz band range. So there are many molecules, many particles that exhibit unique terahertz signatures at those frequencies. That's why they have been investing so much. So let's be careful with the claim. Is there anyone in the terahertz band? Yes, we have those folks. Fine. So what have we been doing as a group with this motivation? And as I said, first with Professor Akildis at Georgia Tech, and then since moving to Buffalo with a group of faculty, Professor Jonathan Bird, Professor Eric Einarsson, Greg Azin here in the city. What are we doing? Well, we're establishing the theoretical and experimental foundations of ultra-broadband communication networks in the terahertz band. What are we doing? Actually, we're doing many things. On the very first hand, what do we need? Well, we need terahertz devices. And part of the talk today will be focused on how do we generate terahertz signals? How do we modulate them? It's great to have a terahertz source, but if you don't know how to add information to it, it's useless for the communication people. How do we make terahertz antennas? And of course, then how we detect this, how we demodulate. In parallel to understanding the devices, we need to understand the channel. So we'll have some works on terahertz channel modeling and capacity analysis. It's only when we know the type of signals that we can generate and what will happen to our signals when we generate them, then it's when we can start talking, okay, which are the best signals I can transmit? So modulation, how can I protect my signals? Coding, what will happen if in really you're trying to communicate really fast? Well, synchronization. Can we go beyond what we know? Ultramassive MIMO. And eventually, down the line, we'll get into terahertz networks. Before going into the details, why I would do this, do we really need these very high frequency, potentially very fast wireless communication systems? Well, let me just spend a couple of minutes on applications, which we classify in two groups. On the one hand, we can talk about macro-scale networking as scenarios. And by macro-scale, I mean the networks that you know. Think, for example, of a Bluetooth on steroids, right? An extremely fast, terabit per second, short distance link. You can use it to transfer huge amounts of data in less than a second. In Japan, for example, they are pushing for this multimedia kiosk in which the idea is that you download entire series or movies before you get into your high-speed train or plane onto your tablet in a matter of seconds. Or, for example, think about cutting the cord in your high-performance virtual reality headset. Other applications, of course, is to move towards small cells, Wi-Fi, with the terabit work in front. Again, we are not going to the terahertz frequency just because it's higher frequency. We are moving there with the promise of the bandwidth. As we know already from millimeter wave, however, we'll need directional links, and that will bring some interesting networking challenges. If you look at who is sponsored this work, well, the military have their own interest in terahertz frequencies for several reasons. We're talking about different frequencies. We're talking about potentially huge bandwidths. Fine. And, you know, we mentioned NASA first. We actually have even ideas that go beyond that. So we will learn that one of the main problems at terahertz frequencies is absorption. How about we go to a place where there is no absorption? How about we use terahertz for satellite links? That's an idea that we have been developing with Professor Akildis in the last few months, and things are coming up. Of course, these are applications that some of you may say, okay, these are like improving what we already have. Can we do something even more different? And that's when we talk about nanoscale communication paradigms. Why? Well, because when you go to terahertz frequencies, your wavelength becomes really small. I'm talking about tens or hundreds of micrometers. Your antennas become potentially very small. Your RF circuits become potentially very small. So you can start talking about doing things that before we couldn't. And for example, we can talk about wireless networks on chip. Think of your computers. For the last 10, 15 years, your processor has been operating at few gigahertz. You say, oh, but every time I buy a computer, my processor is faster. Yeah, it's not because you have faster processors. You have more cores on chip. If you talk to Intel, and some of you I know do, well, you know that they are moving towards massive core architectures in which you have on chip maybe hundreds, if not thousands of cores. How do you connect them? Well, they started doing the simplest thing, a shared bus. But you know from your networking class that, you know, an Aloha or CSMA on a shared bus, it's not the best thing you can do. So they are moving towards a wireless network on chip. They will say, oh, but the footprint of a radio in the chip doesn't really make sense. Well, maybe you're not at the right wavelength. Let's go terahertz. Another application, when you get to these frequencies, when you get to terahertz frequencies, you start to interact with biological systems. One of the projects that we have currently going on, funded by NSF, but with Roswell Park, which is our largest cancer research institute in West New York, we're working on the utilization of terahertz as an interface between intrabody implants, which are biofunctionalized, in this case, to detect early cancer indicators, and eventually to communicate with a wearable device that could potentially then collect data into the cloud. So these are things we're doing. We can use terahertz for sensing. Great. What's even cooler than sensing? How about actuation? Can I use terahertz signals not just to see, but to push, to pull, to control living processes? So again, it started as a crazy idea, but NSF likes crazy ideas. So we moved, can we actually use terahertz or close to infrared or optics, somewhere in between, to control cellular activities? And we're doing that through optogenetics and very small optical devices. Of course, maybe I presented this as two separate walls, the macro wall and the nano wall. Well, in reality, everything is interconnected. So we can think of devices in and out of the body, in and out of your electronic devices, everywhere, interconnecting, from nano to macro. That vision, it's why, actually 8 years ago, we published as the Internet of Nano Things. And in 2010, talking about these nano devices, talking about interfaces between nano and macro, talking about what's kind of thought, you require a visionary to see this. That's what we did, and well, today this figure makes perfect sense. At this point, hopefully, you're all convinced, okay, the terahertz band looks great. So Josep, why is not everyone working at terahertz frequencies yet? Well, we have a problem. The problem is we don't have a technology that really works well for terahertz. Why? Well, strictly speaking, what we don't have is a clock. In other words, it's very difficult to generate high-powered terahertz signals. Why? Well, think in the following way. How do we generate a microwave signal? We have an oscillator, right? Or if we need a millimeter wave signal, well, now we have ways to generate the millimeter wave signal, or we can multiply a microwave signal. You will say, okay, I will keep multiplying and I will get to terahertz. Yes, you can do that, but as you will see later on, the power you get is very low, because every time you multiply, at the very least, you lose half of your power, if not more. You'll say, oh, I'll have an amplifier. Well, good luck finding an amplifier at terahertz frequencies. Then you will say, oh, I'll come from optics. I'm going to use, photomixing, and I'm going to down-convert to terahertz. Yes, that's a way to do, but once again, at the very least, you are dropping half of your energy, and it's fantastic. Okay, you can start from photonic signals, but then to manipulate them, to modulate them, to encode them, you will have, again, to go back to electronics, and the electronics are not really there. So what can we do? No, I mean, Josep, you're coming with a problem. Well, I'm an engineer, so we are supposed to solve problems. So look, for the last 10, 20, 30, 40 years, there have been billions of dollars, billions of euros, billions of any currency you can come up with invested into nanotechnologies. And what has been the outcome out of this? Well, it has been very nice science paper, very nice nature papers, but how about for the real society? Well, for me, as an engineer, as the gap between fundamental physics and the society, nanotechnology has provided us with tools with which we can create new type of materials, new type of structures with, new designs, new materials, and eventually new physics. So one of those materials is actually graphene, and I'm sure that many of you have heard it. So graphene was the first two-dimensional material. What do I mean by two-dimensional? It means that it's one atom thick. You will say, oh, come on, this is 3D, reality is 3D. Yes, it's a 3D material, but it's just one atom thick, so we call it two-dimensional material. Graphene, it's actually not a new material. It was investigated since 1859. But it was not until 2004 that André Geim and Konstantin Novoselov were able to experimentally obtain and characterize graphene. For that, they got the Nobel Prize in Physics in 2010. Graphene has been the cover page of many Nature science issues, many articles. But what does it mean for me? Well, it's a material with excellent mechanical properties, electronic properties, and optical properties that we can leverage to create different types of devices. At some point, around 2010, 11, in Europe, they invested 1,000 million euros, so $1 billion, into graphene as a flagship project. Some of these things have not come to fruition, mainly because in graphene it's difficult to engineer a bandgap and to have an on-off behavior that would allow you to make a processor, but some of them actually have been extremely helpful. And it's in the context of graphene that we're going to show the work that we have been doing, which is, can we use graphene to make transceivers and antennas that implicitly work at terahertz frequencies? Well, that's what we think, and that's what we're going to show. The key idea here is the following. I'm not talking about an electronic device. I'm not talking about a photonic device. I'm talking about a plasmonic device. What is that? We'll talk about that in a couple of slides. So in the vision that we have, in the system that we have, what do we need? We need a way to generate a signal. We call it a plasmonic signal that occurs at terahertz frequencies. We need a way to add information to this signal. You will see many people working on terahertz sources, but then if you don't add information, That's half of the story only. And then we need a way to radiate this signal. Of course, this signal will propagate as a free space electromagnetic wave. We need to recover it. We need to detect it, demodulate it, and hopefully restore that information that we lost. So let's go element by element. I started this talk by saying we don't have a terahertz source. Or do we? Well, it was already in 2014 that we proposed the idea of an on-chip terahertz plasmonic source. You can think of it as a nanotransmitter, which is both a source and a detector of terahertz radiation. It's based on a high electron mobility transistor in which we did some fine-tuning of the boundaries, and which we built using 3-5 semiconductor materials. Some of them are actually very similar to the materials that you're growing or synthesizing here at NYU. And the key idea is enhanced with graphene. You will see what I mean by that. For these ideas, not only we published, but we understood that there is a huge opportunity. So we also patented these ideas, and we got the patent a couple of years ago. So the question is, we know that 3-5 semiconductor materials are not necessarily the best plasmonic signal carriers. They are not necessarily the best materials in which we can propagate signals. The answer to that is that I'm using the 3-5 semiconductor material to source, to excite that plasmonic signal. But then I'll carry it away, not necessarily far, with graphene. That's a very good point. Let me go through it, then it will be clear. So the key idea is the following. Imagine the following device. This looks like a transistor with a source, a drain, and a gate. We know that if I apply a DC current, so nothing here is beyond DC current between the source and the drain, electrons will start to flow. If this is a 5-3 semiconductor material, here I will have a two-dimensional electron gas. And in that two-dimensional electron gas, electrons move quasi-ballistically, so they smoothly propagate through. I usually tell my students, think of this as an ice skating ring. You come here, and then you glide through the drain. Now imagine that I make this ice skating ring in the following way. I have a huge door to enter in, but I make a tiny door to leave. So you are happily coming into this ice skating ring, but only some of you will make it out. Of course, if I close the door, there is no current, the device doesn't work. So I need to make sure I leave a door. What will happen? These electrons will come in, some of them will glide, some of them actually will bounce back. So by finding the right impedances, that's what I mean by doors, at the source and the drain, with the right 3-5 semiconductor material, with the right density, with the right velocity, with the right length, I can actually turn this into a resonant cavity. Is this something new? No, actually, this is something that Diakonov and Schur demonstrated in 1997. And you will say, okay, then what's the novelty? How can you get a patent on something that someone else did? No, actually, that's half of the story only. So in all those devices, the key idea is to have a metallic gate. What happens when you have a current oscillating at any frequency, let's say terahertz, but it's hidden under a metallic gate? Well, you don't see anything. At most, you see what leaks out from under the gate. So the key idea for us was to replace that metallic gate, to utilize something that can look as a metal if we need to, in this case graphene, and then to use that to extract this energy from the two-dimensional electron gas and then carry it away towards wherever it's the next thing. Of course, I know Shalou will say, oh, but you know, graphene cannot propagate signals too far. Well, I'm not trying to go several wavelengths. I'm actually just trying to get half wavelength apart, or maybe one wavelength apart. So the key idea, how to couple the energy from the confined plasma wave, think of electrons oscillating here, to a surface plasmon polariton wave, think of electrons moving here, and the electromagnetic mode that goes with the oscillation of the electrons, that was the key of the invention. Let me move on. I said, of course, this is how you generate the signal, but if I want a communication system, I need to modulate it. I need to add information to it. Should we mix? Should we bring some mixer type of problem? Well, maybe not. Maybe what I should do here is, look, graphene is many things, and it's also not many things. But one of the things that is useful for me is that graphene is a tunable material. I can apply different backgate voltages and, for example, change its Fermi energy. In other words, I can change the propagation properties of this material, so wave propagate differently on this material. So what we did in this paper is just think of a simple waveguide in which there is a layer of graphene through which your surface signal propagates. And let's see if I can control the phase. And moreover, let's see if it's good enough that I can even start talking about symbol error rates, which is what we need for communications. So the key idea here is the following. Imagine you are a bunch of electrons moving that you have been exciting at a given frequency, and then you go through a waveguide. But now think in the following way. If I can change the material properties of this part of the waveguide, how can I do that? By applying a voltage, I can actually speed up this wave or slow it down. If I'm always looking at the output at a given sampling frequency, the phase with which my wave will leave this structure, it's only related to the speed at which it went and the length of this. So I can modulate the phase by modulating the Fermi energy of this graphene layer. That's a simple idea, but again, this is showing me that I can modulate its signal when it's already at terahertz frequency. So it's a terahertz modulator. Fine. Of course, eventually I want to radiate this, which means that my signal needs to be somewhere where I can, convert it into a free space electromagnetic wave. And this is actually goes the other way around. So this is something that started my first year of PhD, that then we published originally in 2010, took some time to get it into a journal, took 7 years to get it into a patent. So what's the key idea here? Well, if I can engineer the boundaries of a waveguide, I can make it a lossy cavity. So actually, I can make sure I can radiate it. So one of the things we showed here is the following. If I have my signal coming in, what does it look like? Well, this looks like a patch antenna, a nanopatch antenna. What is this made of? We have the graphene layer, we have the same supporting dielectric. I really love when there are people talking about graphene antennas, and they talk about the graphene levitating. No, that doesn't happen. Graphene needs to sit on top of something, and actually one of the challenges is how you make this dielectric to make sure graphene keeps its beautiful properties. And then we can engineer this to radiate. Because of the way in which surface plasmon polarity and wave propagate, I can end up making an antenna which is even smaller than the wavelength and efficiently radiate in the terahertz band. The ultimate vision would be to have your source, your modulator, your antenna at scale.
Josep, I have one more question.
Sure. No, please.
So what's the power that you're radiating?
That's a very good question, and I will answer that. You're always ahead. Good. So till this point, you're saying, OK, Josep is great at having ideas and making PowerPoint figures, but what else, right? Well, one of the challenges, one of the main objectives, especially in the last few years, has been, OK, we need to show that this works. So how do we do that? Well, the difference is that we know what we want. We want terahertz communications. And we do have some ideas, but we need to build the theory for them. Some of these ideas require working with materials, and for that we incorporated material scientists in the team, Eric Einerson. Some of these ideas then require device integration. So for that, we have 2D materials, we have graphene, we have 3-5 semiconductors. How do we integrate them, for example, in a transceiver, in a modulator, in an antenna, in a front end? And of course, we need to measure, so we need the facilities. And as you can imagine, if I'm saying to generate terahertz signals is hard, how do you have an equipment that can generate them to characterize another piece of equipment? Well, you need money, fine. So what have we been doing for the last few years? Well, we have improved our analytical skills to actually model that indeed we can have this coupling between the two-dimensional electron gas and the graphene layer, taking into account that, in addition to the impedance of the source at the drain, eventually my signal is leaking. It's leaking out either towards the modulator or to start even towards the antenna. So we need to do the theory that I will not go in detail to, but we had to put electromagnetics a little bit on the side and look into electron transport, which at the end, my background is wireless communication. So it requires some effort, but we're doing that. And we can predict how to engineer the antenna impedance to make sure that we can still have instability, at least over some frequencies at terahertz. But that's just theory, and as many of you know, when you do pure theory, at some point you need to make simplifying assumptions. So before going to experimental validation, can we build some simulation platform? Once again, some of you, for example, if you are in RF design, you are familiar with CSTs, HFSS, COMSOL. They are all very nice simulation platforms. But can they really handle more than one physics? You will say, oh, COMSOL is called COMSOL multiphysics. It's supposed to handle. Well, yeah, but then when you start looking, you will see that they cannot really handle, and after spending time and money, you realize that, well, I need to come up with my own platform. So one of the things we have been doing in the last couple of years is to come with our own simulation structure that combines both Boltzmann transport equations for this instability process, we call it the Dyakonov-Shure instability process, as well as Maxwell's equations. The challenge is that there is no platform, so we made our own. The key idea, once again, is that, look, when you make a COMSOL simulation, an HFS simulation, you usually start by defining your material properties. Here, what I'm trying to say is that, well, my material properties are the ones that are not static. If I'm trying to model an unstable process, I need something that can describe it in time. In that case, we took the hydrodynamic model, and in this model, there is a component which is the electric field, and that electric field on its turn depends on Maxwell's equations. So I keep updating one and the other in a loop, in a discretized structure, in a discretized system. What do I get out of this? Well, I get to a point in which I can run simulations like the following. What happens when I have a source and a drain, a given gate, and I apply a DC current? based on the type of 3-5 semiconductor material that I'm used, based on the mobility, on the relaxation time, based on the drift velocity, I might end up in a system that dies, so this is not the type of source you want, or by changing those parameters, I can end up in a system that suddenly kicks in. And what suddenly kicks in, this is giving you your terahertz carrier signal. So we are at a step in which we're going beyond the state-of-the-art in simulation to come up with a platform that now we can use for other things. And the student who did this, who, by the way, is in the market, has acquired a set of skills which are really useful for a terahertz device group. Of course, this is not enough, and as we said, we need to go to fabrication. So one of the very good questions is, what type of materials are we going to use? In Buffalo, we don't grow our own materials. We actually collaborate and get those materials. We have some of them coming from Japan. We have some of them coming from Austria. And we try with different materials. At the end of the day, if your mobility is not where you are, you may end up having to go at cryogenic temperatures. But, well, that's under the promise that eventually you don't need to do that. And, of course, again, I'm a wireless communication person talking about with my students, doing different type of fabrication processes, working with Professor Bird, Professor Einarsson to do this. Their students are the ones that live in the clean room. And creating structures, which, again, I will not be able to show much more, but this is one of the structures we built, in which clearly what we have here is a source and a drain. And what you see down here, these are actually the gates. This is actually a 2-gated device. And what you can see, think in the following way, think of electrons coming in avalanche mode from the drain, from the source, but then having a difficulty of getting out through this tiny drain towards the drain contact. So these are things we have been doing, and as we speak, we are characterizing some of these figures, and hopefully within a couple of months, we can have experimental proof of an on-chip terahertz source, which is not necessarily larger than 1 by 1 micrometer. That's the type of terahertz source that down the line, I'm not saying you're going to use this next year, but down the line, it's what you may have in your cell phone, it's what you may have in your medical devices, it's what you may have somewhere. Of course, when it comes to two-dimensional materials, it's again with Professor Einarsson, he is able to grow high-quality, large sheets of graphene through their processes that they have improved, so we can do this in-house, which is great, and we have built different type of antennas in different shapes. These are actually different designs of antennas. The first step is to characterize the graphene still conserve its properties when we start shaping it, and of course, the next step is to measuring that. Takes some time as someone who is transitioning from theory to simulation to fabrication and characterization. You can only do this with the right team of people, and that's why, it's so important to have the right resources all the time. Of course, I'm trying to say one thing here. You will think, okay, so we should go, please, go ahead.
So can you comment, like when you show the simulator for the
Yeah.
gallium arsenide, basically, I can see that the parameters or the material properties. Have you considered the geometry?
That's a very good question. So what we're doing is, well,
Repeat the question.
yeah, so the question is, in these equations, we are showing how to link the different magnitudes, current density, electron density, current, velocity, electric field with electric and magnetic field. But where does the geometry enter the game? The geometry enters the game from the moment that this is a finite difference platform. So what we do is, we describe our geometry, we mesh it, then we have a collection of discrete points on x, y, and z, and then we have a collection of discrete points in t. For every t, for every x, y, and z, we solve for n, we solve for j, under the assumption of an electric field. With this n and j, we use j as the current in our electromagnetic equations. We update the values of E and H, and then we take this E, we bring it back here, and we keep running this evolution in time. So it's time domain, finite difference. The geometry enters in the description of the X, Y, and Z. A very good question.
And power level, are you going to address that later? Transfer power level?
I can tell you right now, because I don't know if I will have time to go to that slide, but at this point we're talking, from a device like this, what we're seeing, and don't call me on that, it's on the order of 100 nanowatts. 100 nanowatts, it's extremely low. We know that. But at the same time, what's the power density if this is coming from 1 by 1 micrometer? Micrometer. So the power level is very low, but at the same time, the device is very small, which can lead to high integration. So we will talk a little bit about this in a few slides, but it's good that you asked for the number. Okay? Shalu, yes.
So we run your hydrodynamic model. So in the hydrodynamic model, what really happens is that the electrons are out of equilibrium with the lattice structure, which would be your indium gallium arsenide.
Yes.
So Boltzmann transport equation do you consider in the hydrodynamic model? That's what I'm getting at.
Okay, well, we're using the hydrodynamic model. We're not using full Boltzmann transport equations, but we're using that coupled with Maxwell. We're not using the Euler equation. So what we're doing is under the assumption that the key idea is the following. This system works as long as your propagation time is shorter than your scattering time. Under those assumptions, you can kill some of the terms of a hydrodynamic model and then show that it works.
I guess you're in equilibrium with
Yeah.
the lattice. That's
Yes.
what I was getting at.
Yes.
Repeat that, you're in equilibrium with the lattice? So
Yeah, so the idea is the following. We are under the assumption that we get in equilibrium with the lattice.
Which means that the temperature of the electron at a given time would be 300 Kelvin, let's say.
Yes, we assume that there, yeah. Room temperature. This is at room temperature, yes. Good. Okay. What I was trying to say here is that at this point you will think, oh, so we should all invest on graphene? Well, relax. I mean, graphene, it's the first two-dimensional material that was known, but that doesn't mean it's the only one. So in the same way that our colleagues in Nanomaterials were doing graphene several years ago, well, what are they doing now? Waiting for us to do a device? No, actually they are looking into new two-dimensional materials like, again, I was talking with the booth earlier today, some other new materials being grown here too, not only individually like MOS2, HBN, but also looking at joint properties of their combination and integration. So there are many new opportunities coming up. So when people come to you, oh, this terahertz, we don't have the devices, we don't have, look, I mean, we don't have the devices now, we're getting there, but the key is the following. If someone comes to you with a problem, and the problem is like, look, this is a constraint from the physics, then it is really a problem. But if someone comes to you and they say, oh, there is a problem, but the problem, it comes from the technology, well, then you're an engineer. You know how to change technology, improve technology. So don't let people say, oh, terahertz might not fly because the devices are not there. They are not there today. That doesn't mean that they cannot be there. We're not breaking any law of physics. So we will get there. There are many exciting technologies coming ahead. Okay. At this point, you may think that I'm a material device person, but the truth is that, I'm an intersection person, if you want to call it like that, in which we also work on signal processing, communication, and networks. And for the next 10 minutes, what I want to show is a little bit of the work that we have been doing in mainly these two boxes. First of all, as a PhD student, 10 years ago or 9 years ago, they say, oh, terahertz is not going to work because you don't have the technology. I said, well, there are opportunities for technology, work with materials, work with devices. Then they say, oh, but the channel is horrible. What do you mean by the channel is horrible? Oh, we know, terahertz, there is this absorption problem. Well, let's look at the terahertz channel. It's really interesting because one of the very first work I had to do was to look for terahertz channel information, and they were always showing this crazy behavior over terahertz frequencies. Then you start tracking where that figure came from, and it was actually hand-drawn somewhere back in the 50s and 60s, and that figure propagated, right? So is this really the way we do research? Well, I hope no one here uses paint for his paper, so, that's... So what we did? Well, let's go and create a channel model, but coming from the physics, so let's use radiative transfer theory, let's use all the data that the HYTRAN database contains. This is a database that contains all the molecular reactions to different terahertz signals, infrared and visible. So this is a very long, extensive database. And let's use that to develop path loss and noise models and to compute capacities. This was several years ago, and this was one of the very first work. So, of course, as in any wireless communication systems, our channel depends on, at the very least, the spreading loss. This is the same as in any wireless communication system. And despite people write it like this or upside down, I like how, to represent it in the following way. So look, one thing is the spreading factor, which means how over what surface your signal is spread. The other is the antenna effective area, which means how much you can intercept out of it. So don't start by saying the terahertz channel is horrible because of the channel. No, actually, maybe because your antennas are small, but we'll get there. The second thing is molecular absorption. What is molecular absorption? It's attenuation due to molecules taking your signal. What do I mean? Well, at terahertz frequencies, several molecules will start vibrating when they are irradiated by a terahertz signal. What do I mean by vibration? I mean that they will exhibit internal, mainly rotation, movements. In other words, you had a molecule that wasn't moving, but from the moment you irradiate it, it starts moving. As you know, energy cannot be created or destroyed, only converted. If these molecules now have kinetic energy, it means that you lost your electromagnetic energy. That's absorption. Question, so does it mean that terahertz is going to kill us? No, we shake molecules, we don't break them. So keep that in mind when people say, oh, we're going to do something. Okay, We'll talk more about these body effects in a couple of slides. So the key idea is that we can compute this transmittance of the medium. There are different ways. The simplest way is to start by assuming that we have an homogeneous distribution of molecules. We kick in with the Beer-Lambert law that mainly tells you that the absorption loss goes exponentially with the distance and the molecular absorption coefficient. Instead of using tabulated values of these molecular absorption coefficients, we went into the details and we look at the relations between pressure, temperature, volumetric density, and the specific molecular absorption cross-section, which I skipped the details because of time, but the key idea is that this specifies different absorption lines as well as different absorption intensities. Going to the results, what I would like to show is the following. In this figure, I'm showing the path loss as a function of frequency and distance, and the color represents the path loss in dB. What am I seeing here? Well, if you're talking for very short distance, maybe on-chip type of networks, sure, you will have a spreading loss, but there are not so many molecules that will absorb anything, so you don't see absorption at here. This is supposed to be a micrometer, that's fine. If you go to longer distances, well, you're starting to see some lines here, some dark blue lines, that means absorption lines, but that's okay, doesn't look any worse than any other channel. Of course, when you start to go to longer distances, you see tons of dark blue. That's a little bit scary, but you also see some light windows. And you will say, oh, come on, but Josep, these are very small windows. Well, excuse me, small depends on when you talk about. One of these windows, again, this was a terahertz axis, one of these windows, it's easily hundreds of gigahertz. So even for long distances, you have tons of a spectrum. So don't let people tell you, oh, the absorption makes the channel useless. No, actually, the channel is nice. You just need to be aware that there will be absorption lines. The beautiful thing is that those absorption lines, you know where they are. The intensity depends on how many molecules you have, in particular water vapor, but you know where they are. And what's more, for some application, get out of the atmosphere, you actually don't have that. So keep those things in mind. Okay, this figure looks horrible here, but this is a summary of some of the absorption-defined windows. What I want you to keep in mind is the following. In those absorption-defined windows, you have, relatively low absorptions. The total attenuation is huge. Why? Because of the spreading loss. So if you are not going to have terahertz signal systems by tomorrow, it's not really because of the absorption, because you know how to get rid of it. It's going to be because of everything else. So, once again, for short distance, the terahertz band is great. It's a large signal, a large band in which we can transmit broadband signals, maybe pulses like what Professor Babakani was presenting 2 weeks ago, or as we increase the distance, we can go to several windows, multiple gigahertz wide each. Of course, this was all line of sight, and as you know, non-line of sight or multipath propagation is extremely important. So there are several works going on, both at Georgia Tech. We're doing also some works of this at the University at Buffalo. These are still mainly theoretical results, so not until you have the platforms you can start measuring. Now we have some platforms we can start measuring. Here you have some platforms we can start measuring. But all these things are moving on. The question, however, is like, okay, so you talked about short distances and maybe up to 10 meters. Can we go beyond that? Because actually the path loss, even at 10 meters, was already 100 dBs. How do we go beyond that? Of course, I can mainly think of two options. One is to increase the transmission power. The other is to increase the directivity gain. Let me show a couple of things. I know that many of you will ask me, Josep, if we had to bet on a technology, or if I need the best technology today, something I can get, what can I get? Well, I would go talk to the guys at JPL and ask them for their terahertz up-converting systems. We're talking about more than 100 milliwatts at these frequencies. This is a state-of-the-art, not what other news articles make you think. These are the bandwidth that we're talking about. So, I'm talking to Mehdi or Jose Siles, you can get some of these. For the second option, of course, you will say, look, you said that the antennas are smaller, so we are just going to put more antennas on the same array. We know that will take forever to control, or it's challenging. We could do that. But let me think in the following way. Okay, we know that our antennas are smaller, therefore we can make dense arrays. Fine. The thing is this exciting? Well, we have MIMO, massive MIMO. Think in the following way. For the last 90 years almost, we have been designing antenna arrays in the same way that they were first proposed. We're mainly talking about half-wavelength elements, spaced over half-wavelength distances. Now think with me. In the same way that we know that the minimum sample frequency in time needs to be, twice the bandwidth, but we never sample at twice the bandwidth. We actually always oversample beyond Nyquist. Why today are you still sampling space, which is what an antenna array does? What are you still sampling space at half wavelength? Why don't you oversample in space and start talking about really engineering front waves? So with that idea in mind, a couple of years ago, we were, again, when you need crazy people to work together, so we have crazy ideas. We said, OK, can we actually come with a name? We call it ultramassive MIMO. But the key idea is not to put more antennas, but actually to use plasmonic antennas. What do I mean by plasmonic? The key idea of a plasmonic antenna, as I showed before, is that they are much smaller, not just because the wavelength is smaller, but they are much smaller than the wavelength itself. So for the first time, you can integrate them because they are smaller than the wavelength, but also because their mutual coupling is smaller, and we have shown that in another paper that I will have to skip. But we can actually sample space with much more resolution than your half wavelength. You will say, do we need that? Well, that allows you to start engineering front waves in non-traditional ways. And we are just at the beginning. We actually know how to make this type of arrays. We actually designed some of these arrays in reflection. Why? Because we don't really have the source yet. So can we at least engineer the reflections and gain not just one way or the other through beamforming, but with sub-wavelength resolution, so in crazy ways. Some of you may know about metamaterials. Well, what is metamaterial? I mean, sorry, probably this should not be on camera, but when you talk to people in optics, you see that they like to reinvent things that have been known to the microwave community forever. They talk about metamaterials when they are talking about antenna arrays, but that's fine, we'll give them that. Yes, this looks like a metamaterial, but it's nothing but a sub-wavelength antenna array. Having said that, we are starting to do some channel modeling, how much we can get out of these arrays, taking into account what we already know from the channel, leveraging the results of massive MIMO, and moving forward. For some of the applications, I was talking about Intrabody, and I know about the time. We was talking about Intrabody. Okay. Thank you. So we were talking about Intrabody applications of terahertz. And let's say, OK, look, if we're going to look into the body, let's look it in the right way. First of all, when you model the body, usually people, what they say is like the body is an effective medium with a given permittivity, with a given permeability. But the truth is the following. When you start going to these high frequencies, and especially when your excitation element is going to be equally small, your body is not an effective medium. Your body is a collection of cells, different type of molecules, different type of elements that create multipath, that create a scattering, that create absorption. So making the effective medium assumption might not be the best way to go. So what we started to do a couple of years ago was to look into the intrabody channel, both for terahertz and optics, because if you're not afraid of going high in frequency, much of the theory we're doing works for optics, and try to understand what happens. One of the things that we came across is the following. Actually, remember, think of the typical progress meeting. Your student comes to you, your best student, and tells you, look, I'm doing these simulations, I did this model for signal propagation through individual cells, red blood cells, and I'm seeing something like this. I'm seeing that actually my signal is focused after the cell. OK, probably you did something wrong. He comes with a new set of data. I said, no, I'm seeing the same. OK, probably you did something wrong. Then he comes, look, someone published this in Nature last year. Cells act like lenses. OK, now we're 1 year late. Thank you. So what did we saw? We saw actually that contrary to what people think, biology may actually help us to focus signals. And this is a result that's telling you, from an antenna through a cell, this cell, based on the type of cells, not all of them, but this in particular, it's a red blood cell, helps you focus the signal after it. It acts like a lens. Of course, is this really true? Well, we happen to work with some neuroscientists for that, brain interfacing, and said, OK, let's look at it. And what we did is the following. We took living neurons. We usually work with living cells because their properties, their chemistry is different, whether they are living or not. And what we look is a cell, and we were shining light from top. We are looking at the cell, and we are either focusing on the cell or beyond the cell, after the cell. And what we see here are some dark spots that then kind of look like bright spots. You will say, Josep, we don't see it. OK, let's zoom in. So we can see here some dark spots that then look like bright spots. We're seeing more intensity after the cell than on the cell. So actually, this was motivation to say, okay, something is happening. This, in case you don't know, this is the head of a neuronal cell. These are around 20 microns. And what we are here are the nucleoles, which are heavy concentrations of DNA in the cell. So we have a feeling that DNA is helping us focus, again, signals between terahertz and infrared, which is something very interesting and, makes sense. Of course, then we talked to the people in the neuro school and medical school, and they said, but we always use light, right? Okay, why do you use light? Because lasers are cheap, let's be honest. So why do you use light for imaging? Because look, let's look at how deep you can see. And with light, you get 80, 90 dB of path loss as you try to go through cells, through tissues. So you get this type of system. You say, oh, but at terahertz I get the same, 80, 70, it's a very small reduction. No. Look here, this is over 10 microns. This is over 10 millimeters. So with terahertz signals, we can propagate much deeper. Of course, we will not get the 100 nanometer resolutions that you get with light, but you can get easily 10 micrometer resolution, and if you're looking at body structures, cell structures, that's already enough. I'm not saying that we should move the entire biocommunity from infrared to terahertz, unless they want to, because there are other things to take into account. I explained you that absorption, when you are in free space, shakes your molecules. And molecules in a gas can shake. There is no problem. The problem is that if you're making molecules shake in a liquid or in a solid where they cannot shake, there is friction. That friction becomes heat. So then we have the problem of absorption in the body. So, let's don't rush. Let's do it right, step by step. We are positive that this is possible, but okay, let's convince everyone through the way. And with this, I'm going to just speed up very quickly. We did some works on modulations and coding. Again, you had Professor Babakani 3 weeks ago. He talked about how to generate these terahertz sparks. We actually have some works for several years now in which we introduce, okay, let's use these very short pulses, 100 femtosecond long pulses, as a way to enable communications, just modulating following on-off keying and spread in time. For this was a theoretical paper. We also developed new stochastic models of noise and interference, and through those, we computed single-user and multi-user data rates. Those are works that we have that I invite you to read, and we saw that, through this pulse communication, through interleaving, we can actually get to interesting densities and to interesting data rates. This is great for short distances in which there is no absorption. As you go to longer distances, broadband signals will be chopped because of absorption, so maybe that's not the best thing you can. We do have some very recent work with Dan Mittelman. He will present it himself when he comes here. It's actually, we were doing some, let's say, both measurements and characterization of multipath propagation, including diffraction from obstacles. So we realized that, well, we might be able to intercept terahertz signals, provided that you have the right obstacle, even if very small. You just need to be comparable to the wavelength. You may be able actually to eavesdrop from very directional terahertz links. Of course, we also propose a countermeasure. If not, my Air Force funding would be cut. So other problems as we go to higher frequencies, well, whether it's terahertz or optics, when you try to communicate very fast, remember the original motivation, terabit. One of the problems is that, your symbols are very short, your symbols are very low energy, terahertz clocks, we don't have them, or the ones we have are not the most reliable ever. And let's don't think signal processing is going to solve all the issues, because if you're really targeting tens of gigahertz of bandwidth, you're going to face the problem that the fastest analog to digital and digital to analog converters can only handle up to 100 gigasamples per second. We'll say, oh, that's huge. Well, if I follow Nyquist, this means that my maximum bandwidth is 50 gigahertz. I show you windows with hundreds of gigahertz of bandwidth. How do I use that bandwidth if I cannot sample it? So we need to come up with new ways to overcome this problem. By the way, a problem which is not unique to terahertz. It's the same thing that happens to optical people on fibers too. So solving this ADC, DAC problem can be really a big difference. We had some ideas on how to do that by, again, taking advantage of some of the materials we have, graphene, making some sort of analog synchronization. We're pushing to analog because we cannot go digital, but that's fine. You can check the paper. And the very last things I wanted to say are more related to, okay, can we go up to the protocol stack? Some of you here are systems networking people. So the first question is, Josep, if there is so much bandwidth, do I need, a medium access control protocol? There is bandwidth for everyone. You transmit so quickly that there are no collisions. Do we need a MAC protocol? Well, it's really mainly for synchronization. You already see it at millimeter wave. People in optics have the same problem, so you need synchronization. We have some ideas for that. We are actually talking about receiver-initiated transmissions. So instead of asking you sending to someone, let's wait someone when it's facing you to send. We're talking about combining different bands, and these are all some preliminary ideas that, again, at the initial stage, but make some sense. How about relaying? We're not going to solve the problem at one hop, and there are several benefits of relaying at terahertz frequencies, mainly because the shorter the distance, not only the lower the power, but also the larger the bandwidth. So once again, we really need to optimize what we want to do, also because if we're handling terabit per second links, you cannot just assume that your relay will have huge buffers or memories. And of course, neighbor discovery is going to be a problem too. One of the things that I wanted to say to conclude, it's like we spend some time doing the devices, we spend some time in the channel, we're doing some physical layer. I have many colleagues who are networking people, and they say, Josep, we want to jump into this, but we don't want to spend time learning about the channel, plus the channel is still being discovered. What can we do? So what we did for the last couple of years was to create an NS3 extension, we call it TeraSim, in which we have implemented a frequency-selective channel model for the terahertz band, in which it's not just a tabulated value. Actually, we are computing the spreading and the absorption in real time for the waveforms you define. We give you a couple of waveforms, pulse-based systems or carrier-based systems you pick, but we have tailored the physical layer both for nano and macro, and we have built some ideas of MAC. This is open source, this is available through the website, and this will be contributed to the NS3 App Store. But this is for everyone. Say, look, I don't care about this channel or physical layer. You should, but okay, I respect you. You can start already building some solutions for that. And the very last thing that I wanted to say is like, look, of course, I believe in our terahertz technology, but I also know that the challenges that involve working with new materials. So both to benchmark our devices as well as to start testing, we have created a new platform, which we call the Terahertz Testbed, and was funded by the NSF CRI project, in which, still as of today, we can claim it's the world's first integrated testbed for ultra-broadband communication at true terahertz. By true terahertz, I mean 1 terahertz and above. What is this? Well, it's pretty much an frequency multiplied terahertz source. You will say, oh, you just told us they are not the best. Well, it's the best I can buy with money now. And it's a good benchmark. So we are using this custom-made by BDI up converter source to 1 terahertz with a broadband mixer able to take up to 40 gigahertz signals, which then I radiate and then I down convert. Who are the expensive guy here? It's neither the up converter or mixer or the down converter and mixer. It's actually this arbitrary waveform generator with 32 gigahertz baseband bandwidth, 32 gigahertz, and is this high-performance digital oscilloscope to collect a sample. I mean, he has actually 63 gigahertz of baseband bandwidth. This is how the system looks in a picture. So arbitrary waveform generator, 2 PSGs, 1 for up conversion, 1 for down conversion, DSO. And the key idea here is that we are not only sending signals, we're actually sending zeros and ones. So from zeros and ones, we generate our waveforms, we encode them, we modulate an intermediate frequency, then we send that over 1 terahertz through a chain of multipliers, tiny horn antennas, down convert, store, then we do our signal processing. These, strictly speaking, you can think of it as 2 sets. One is the baseband, the other is the up and down converters. And for these up and down converters, we can use, if you have a better technology, we're happy to throw it there. We might have actually one of them coming soon. Of course, the measurements are shared as NSF requires, and what I wanted to conclude is, look, I think that terahertz communication will be a major part of 5G or beyond 5G, 6G systems, as FCC comments last week. Some of the 100 to 103 gigahertz systems are all ready to be utilized in practical setups. Doesn't mean that you will have them in your cell phone. It means that you can start doing testing, and that's extremely important. When it comes to really getting to 1 terahertz, 2 terahertz, that may take some time, but it's not impossible. And the key idea is that besides the technology itself, the terahertz band is not even regulated. There is work at all the layers, devices, communication, standardization, regulation, which makes it, for us engineers, some extremely exciting years ahead of us. So with all this, thank you very much for your attention.
Wow, thank you very much, Professor Jornet, for that terrific talk. Do we have any questions for Josep? Ojas?
What do you do about the grating loops when you bring the anti-elements very close together?
Actually,
Grating lobes
So
from
the
the
question is
antennas.
about grating lobes from the antenna. Remember, the grating lobes appear not when you put the antennas too close, but when you start to putting too far. Why? Because you are undersampling. When you put the antennas too close, what you have is mutual coupling. That's the better question. But we showed that with these plasmonic structures, actually the mutual coupling is on the weak side. So we can put them closer than half wavelength. But that's a very good question, yeah.
Anything else? Okay, let's give Professor Jornet a big hand. Thank you for coming. Terrific talk. And we have a presentation for you. Our
wow.
department chair, Ivan Selesnik,
Thank you.
is happy to present
Thank you very much.
a plaque commemorating this talk, and thank you for being part of the Terahertz series, Circuits,
Thank you.
Terahertz and Beyond. Again, a big welcome and thank you to Professor Jornet.
Thank you.